Section 13.4, Ways of Expressing Concentration. If I were to be rude and tell you that your lemonade is weak or too strong, or your coffee is too strong, what I'm doing is talking about a solution. And I'm not giving you specific numbers. I'm not telling you exactly how concentrated, how much coffee bean oil is in the water, or how much lemon juice is in the water, or how much sugar is in the water. I'm just telling you that it's weak or too strong or too sour or too intense. So these are qualitative ways. So qualitative is just generic words expressing concentration. So it's not, so there's no numbers or math involved. Just the idea of whether something is weak or strong. So if I were to use words like dilute, okay, lots of water added somehow, or lots of solvent added, or concentrated, I could tell you that your dish detergent was concentrated. That would give you the idea that there's very little water and lots of stuff dissolved in it. Okay, that's qualitative. Quantitative gives you the idea of quantity. So this is quality. And then quantitative has the idea of math. Okay, so you're using numbers. And this gives you the idea of quantity. So if I were to say that there's exactly this many grams dissolved in this many grams of the solution, or this many grams of the stuff dissolved in this much water, that's numbers that you could actually replicate that. Okay, so that's a quantitative. So we're going to look at 4 different quantitative types of expressions for concentration. The first one we're going to do is mass concentration, which is really easy because it's simply mass. It's mass of the solute divided by the mass of the solution. So we'll talk about that in a second. Then the second we're going to talk about is mole fraction. And you've got a fraction where it's not mass over mass, but it's moles over moles. Okay? So you're going to have moles of the solute divided by the moles of the solution. Okay, so that's kind of the same as mass, just using moles instead of mass. The third one we're going to look at is molarity, which we've seen before, which is moles over liters, moles of solute divided by liters of solution. And then the new one that we've never seen before is called molality. And I used capital M for molarity and lowercase m for molality because since they both start with M, the capital M is used for molarity and the lowercase m for molality. And I'll show you why. Molality is also using moles, but instead of liters of solution, which is a volume, they're giving you a mass, the mass of the solvent. Okay, and we'll see why that's necessary in a minute. So the first one we'll look at is the mass percentage. So if you say, what is the percentage of right answers that I have on my test, I take the number right divided by the number possible, and then divide that and multiply it by 100%, and that gives you an average for your test. You got an 80 on the test, you got a 90% on the test. So if you want a mass percentage, you're simply going to take the mass of some part of a solution. Okay, so I've got something dissolved, I've got something else dissolved, I've got something else dissolved. So let's say I have Kool-Aid, I've got sugar, I've got dyes, I've got citric acid, which makes it tangy, I've got some flavorings. All those have different parts. So you take the mass of each, divide by the total mass of the whole solution, including the water, and you'll find out how much your percentage of a glass of Kool-Aid is your red dye, something like that. So it's going to be the total mass of one component divided by the total mass of all the components together, divided and multiplied by 100. Now a similar idea or another mass percentage that's used is parts per million and parts per billion. This is mostly used in environmental science. If you're talking about how much contamination or how much pollution can you have in a river, or how much stuff can you have in the air, or how much stuff can you have in the water, there are agencies that kind of monitor these things. Instead of using 100, which is parts of 100, they're going to use a parts of a million or parts of a billion, and say how many component molecules in the air can you breathe in so much air. So if you do parts per million, rather than multiplying it by 100, you're going to multiply it by a million. And if you're doing parts per billion, rather than multiply it by 100, you're going to multiply it by a billion. Now, it's not percentage anymore, because remember, a percent sign is times 100%. It's parts of 100. That's what percent means. There isn't a symbol for parts per million. They just call it ppm, and parts per billion is ppb. So it's exactly the same. Mass of the component divided by mass of the total mass of all the components in the solution, times parts per million would be 10 to the 6, which is a million, or parts per billion 10 to the 9, which is a billion. The third useful one, and useful in different ways, is the mole fraction. So it is simply the relationship between the moles of something you're looking at that's inside a solution and the total moles of the solution. Okay, the full moles of the solution and the parts of that. Now, this is very useful in gases. If you have moles of gas and it's made up of different moles of gases, so let's say air is made up of oxygen and nitrogen and argon and all kinds of different components of gases all kind of whirled together, the moles of one would be easy to pick out of the moles of all, since they're just summed up. So you'll see that with gas pressures, mole fractions. So moles of one divided by moles of total. The next one is molarity. Extremely useful. We've seen molarity a lot. Molarity is talking about moles, which allows you to go in through the periodic table to go to grams, so you can find out how much stuff you have very easily, and also volume. So you can use that if you have the density of something. So if you have the density of something, which gives you a volume and a mass, you could easily use that to find molarity. Molarity is just a concentration where you're using a very useful mole idea. But it's also talking about volume. So moles of solute, what you're dissolving, divided by liters of solution, total solution. So liters is a volume. One of the things that is a little bit of a nuisance with this is that as temperature changes, your volume changes because density changes. Something is going to be more dense when it's cold, less dense when it's hot. That's why hot air will rise and cold air will sink. So if you are doing anything that deals with temperature, this is not a really good, even though the molarity tells you how much stuff you have in a certain amount of solution, if your solution, say, has a change in temperature, this was a little bit weird because you can't, as temperature changes, your volume would change and it would mess up your numbers. So we'll see that there's a final one called molality that, instead of dealing with volume, deals with mass, and mass doesn't change no matter what temperature it is. And if you have something like say, melting ice with salt on the road, to where you're changing the temperature of a solution, you would measure something in molality rather than molarity. But molarity, capital M, is moles of solute over liters of solution. Final one, molality, is denoted with a lowercase m, normally italicized, and it's moles of solute just like molarity, but instead of volume, liters of solution, you're going to have kilograms of the solvent. So what's the mass of the solvent? And the mass of the solvent doesn't change no matter what temperature it is. So that way it's more consistent if you have some temperature dependent things. So we'll see that if you say put water in your radiator and your car overheats, that if you were to put something thicker than water, it allows it to go a higher temperature and it doesn't boil over as fast. And so you don't really put water exactly in your radiator. You put antifreeze, which will allow it to not freeze when it's cold, but also not boil over when it's hot. So, of course, since this is quantitative, we're dealing with numbers. These numbers can be converted from one to another. So if you know the density of a material, and density is volume and mass, well, then you can go from molality, which is a mass-based, to a molarity, which is a volume-based. And you can just change it around as you know the differences.